Hi, this is Professor Bertozzi. Again, we're continuing our series on linkages, and we're going to be talking about some new topics in this video. The topics will be the Grashof condition, inversions, toggle points, and transmission angles. So we'll start with the Grashof condition. The Grashof condition is, or the Grashof equation is used to determine whether or not at least one link in a 4-bar mechanism can do a complete revolution relative to the ground plane. So the equation is shown here, S plus L equals P plus Q. Suppose we have just 4 arbitrary lengths in terms of the links, and S stands for the shortest length, or is the length of the shortest link, and L is the length of the longest link. This equation, there can be 3 possibilities. One is that S plus L is less than P plus Q. So this would be called a class 1 kinematic chain. In that case, we're guaranteed that at least one link will be able to rotate completely a full 360 degrees relative to the ground plane. The class 2 is when S plus L is greater than P plus Q. So the shortest plus the longest, the sum of those 2 lengths is greater than the sum of the other 2. That's called a class 2 kinematic chain. In that case, we know that none of the links will be able to do a 360 degree rotation relative to the ground plane. And then finally, class 3 is when S plus L equals P plus Q. And we'll look at some examples of that special case as well. Next, we want to define the inversion of a Grashof 4-bar. So in this case, we get different motion with the same 4-bar by grounding a different link. So of course, if relative to the links themselves, if you were, for instance, if you were standing on one of the links looking at the other links, the motion is unique. It only moves a certain way. But relative to the ground, if you ground a different link, then you do get a different type of motion. So if we first ground an adjacent link to the shortest link, as shown here, you can see that we end up with non-distinct crank rocker inversions. So in other words, there are 2 links connected to the shortest link. If we ground either of those links, so those are the links that are adjacent to the shortest link, we get what's called a non-distinct motion. You can see here it looks very similar regardless of which adjacent link you ground. On the other hand, if we ground the shortest link, then we would get a double crank. So relative to the ground, the 2 adjacent links can rotate 360 degrees relative to that shortest link, which is grounded, so that's relative to the ground. And then lastly, if we ground the link that's opposite the shortest link, we get a double rocker inversion. So in that case, the shortest link will still rotate 360 degrees relative to the ground, but the 2 adjacent links to the shortest link will just be rockers. So we want to look at class 3, the case of a class 3 kinematic chain now, where S plus L equals P plus Q. And you can see that one case would be when the 2 shorter links both have the same length and the 2 longer links both have the same length. Really what you have then is just a parallelogram. But every 180 degrees in that type of 4-bar, you get to a point called a toggle point, where the 2 links are collinear, and they could actually rotate. They could either change direction, as you can see here. So a common mechanism that you've probably seen before is on like a steam engine. If you're driving one wheel and you're using basically a 4-bar to connect it to and drive the other wheel, every 180 degrees, the other wheel could actually change direction. At high speeds with a lot of inertia, of course, that wouldn't happen, but at slow speeds it might. So what you do in the train engine is actually on the other side of the engine, they're out of phase. So in other words, if they're 90 degrees out of phase, the wheel on the other side is going to keep it driving in the right direction at that toggle point. But you can see in this figure where you would have what's called an anti-parallelogram form, so that when you reach that toggle point, it could actually go either way. Another way to deal with this problem is you can add a fifth link. So now, in a sense, you have two parallelograms as shown here, but the parallelograms are out of phase. And then finally, we want to, another case of this class 3 is when you have the two short links connected together at a joint and the two longer ones connected at another joint, as you can see here. So you end up with what's called, you get this kite or deltoid form. It's pretty interesting, and as you can see the motion here, it's kind of an interesting motion. So that's the three different classes of kinematic chains, 1, 2, and 3, where class 1 is Grashof, class 2 is non-Grashof, and class 3 is Grashof, but it's kind of a special case.